This question is about two apertures through which water is passing. Wave fronts represent crests. So the lines here show you the crests of the waves of water as they go through the gaps this way. So this question is about interpreting these wavefront pictures and being able to translate them into your normal wave diagrams. It asks, at which point will the displacement from the sea from equilibrium value be 0? Well, let's have a look at what these waves actually look like. If this is what a wave more or less looks like, then the crest wave fronts, these bits here, equate to the crests. And so therefore the troughs would be in the center between one crest and the other, right? So this would be equivalent to a trough, and this would be equivalent, in the middle, would be equivalent to a trough instead. Now, the question asks, at which point will the displacement be equal to 0? So what we're thinking about here is destructive interference. So we're looking at a point where a crest meets a trough from a different wave. So here we're looking at where a crest meets the middle of the other wave. And you can see the only place that happens is here. Here we've got the crest of this wave meeting the trough of this one. So you're getting that destructive interference. Right, question 6. And quite a convoluted question it is too. This time you have two loudspeakers, identical sources of sound. Now by identical, we mean coherent. So what we're looking at, because there's two, we're looking at a double slit experiment simulation, or the use of the equation for Young's double slits, as we can see here. So this is what we're going to be using. Now it says that there is sound of wavelength 1.08 placed at a distance of 1.8 meter. So capital D, large D, is 1.8. The first source is 0.6 meters above the floor. So this is really interesting because they're mounting this vertically, right? So this is Young's double slits experiment using sound and considering the vertical motion, right? The vertical positioning, not the horizontal. That's what makes it a bit weird. So it's telling you that S1 is 0.6 meters above the floor, and the second source is at 1.2 meters. So this distance here, which is little d, is equal to 1.2. So we have capital D, we have little d, and we also have the wavelength, which is 1.08. Now it asks, at what is the lowest height from here at which you would get a minimum? Right? Now let's have a look at what should happen. The sound waves from here would expand. The sound waves from here will expand, and I meant to say expand and travel. And you should get a point here in the center, always in between the two sources, where you get a maximum. So we call a bright point, a maximum, a place of maximum superposition. Now, using the equation, we're looking at this particular part of the equation. S is the distance between maximum and the next maximum, right, which is equal to S. The question itself, though, is asking about something different. It's asking for the distance at which there is no sound. So it's asking, where would the minimum be? The minimum would be in between these two maximums, right? Because in between two bright fringes, you would get a dark fringe, and that's the place we're looking. So the way we're going to calculate this is we are first going to work out S, which is this distance. Once you've worked out S, which is that distance, you can divide it by 2 to give you this distance and this distance. Now, if you know that this height is equal to 1.2, because you can see here from the bottom to here it's 0.6, and then from here to the middle where the maxima is, it's 0.6. So all of that is 1.2. You can easily find this distance. So that's what I'm going to do next. I recommend that you give it a go now that you know how to work it out and see if you get the same answer. So if we write the equation, and we fill in the values, and then we should get a value of 1.62 meters. So that means from the center, where the first maxima is, to the next one, we have 1.62 meters. Actually, let me just draw that all the way over here, because it's actually a humongous distance, isn't it? It's all the way over here. But now we need to divide it by 2, because we're not interested in the maxima, we're interested in the minima. So somewhere here. And that should give us, if we divide this by 2, a value of 0.81 meters. Okay, so if you see it up there on the diagram, now if we have a distance here of 1.2 meters, because this is 0.6 plus 0.6, then we can work out our value by simply subtracting our 0.81 value from 1.2, which gives us an answer of 0.39 meters. Okay, so that means that from the floor to here, it's 0.39. So there's definitely a lot to do for a few marks, but well done if you get it.